Marhaba. This session is the introduction to a field in mathematics called number theory. Remember, we talked about mathematics, especially pure mathematics, has several fields like logic, set theory, graph theory, algebra, and today we want to take an introduction, to start an introduction about number theory. Mainly, what is number theory? It is the study of integers, okay, the study of the integer numbers, okay, of integers. And remember what symbol we use, z, to denote the set of integers. And so our set Z, this is the set containing all the integers, negative, 0, and positive integers, okay. So we want to focus in this chapter in studying these numbers, these objects, the world of integers. Let's start with the very main definition of this chapter. We will base all of our further complicated concepts on the concept of divisibility. Okay, so definition. Now we say let choose any two integers from here. So let m and n be integers. Okay, then we say that m, the integer m, divides the second integer. Okay, divides n if and only if there exists another integer. Okay, there exists, say, k in Z, such that n is equal to k times m. Okay, so read this again. M divides n if there exists an integer k such that k times m is equal to n, which means that we can approach n using k many m's. Okay, so if we think of n as a positive integer, so say this is the number line of the integers, and say n is here, okay, then let me say n is here, it's a positive integer, and what we want to say that we can take, say m is 3 and n is 9, then we take the first step of length 8. So we start at 0, we take a step of length m, and we reach m, the integer m. Take another step of length m, we reach 2m, right? And then take another step and we reach 3m. We keep taking steps of length m until we hit n. Okay, and then at which step we hit n? After k steps of length m. So after k times m, we hit the integer n by taking steps of length, each of length m, and we take k many of them. Okay, again, m divides n if there exists an integer such that we multiply m by k and we get n. Okay, so this is divisibility. And now let me tell you what is the notation. We write m and then a vertical bar n to say that m divides n. Divides n. And in predicate logic, so what does it mean? If and only if there exists a k in the integers such that n is equal to k times n. Okay, so this is the notation. And if m does not divide n, which means you cannot find such an integer, then we just write m and then cross the divisibility out. Okay, so m, this is m does not divide n. Okay, what else? And if m divides n, we also say that m is a divisor of n. So m is a divisor of n. We also say that n is a multiple of m. Okay, multiple of m. and we also say that n is divisible by m. So n is divisible by m. So all of these say the same thing. Either you say m divides n, or m is a divisor of n, or n is a multiple of m, or n is divisible by m. Okay, and so let's take some examples. Let's start with this. Say 3 divides 12. So notice divisibility, this statement is a predicate, it's a proposition, it's a statement which is either true or false. So this statement says that 3 divides 12. This is true. Why? Because we can, it's a true statement because we can find an integer k such that n, which is 12 here, is equal to k times 3, and k here is 4 times 3. Okay, so since we managed to find 4 such that we multiply it by m, we get n, then this is a true statement. And see here in the number line, we can start with 0 and then take steps of length 3. So take the first step of length 3, we arrive to 3. Take another step of length 3, we get to 6, and then to 9, and then the last step, the fourth step of length 3, you get to 12. See, this is the first step, this is the second step, this is the third step, and this is the fourth step. So we get to 12 after 4 steps, each of length 3. Okay, another examples. Okay, for example, 5 divides 25, because we can find an integer k such that 25 is equal to k, in this case k is 5, times 5. Okay, another example, for example, 7 divides 14, because we can find an integer such that 14 is equal to 2 times this, so this is the integer 2, okay, times 7. What else? For example, do you think 8 divides 0? Again, what does it mean that 8 divides 0? This is true because we can find an integer such that 0 is equal to this integer times 8, and this integer is 0. So this is k, this is m, and this is n, and we say m divides n. Okay. Now negative 4 divides 24. This is true again because what? We can find the k such that 24 is equal to this k times negative 4. What is this k? It's 6. 6 times negative 4 is 24. Okay, now 14 does not divide 7. So why? Because look, if 14 divides 7, then we can find an integer k such that when we multiply it by 14, right, we arrive to 7. But this is impossible. I mean, again, if intuitively, this means that this is the starting point 0, and this is the number 7, say. Now we need to get to 7 using steps of length 14. But if we take one step of length 14, we will jump over 7. We will never hit 7. Okay? And notice here, what does it mean that 8 divides 0? It means we can get to 0 using 0 steps of each of length 8. Okay? This is the meaning of it. So we don't take any step and we get to 0. Okay, this is for the divisibility. Now concept, again let me remind you that we say an integer m divides n if and only if there exists an integer k. Okay, so k is an integer such that n is equal to k times n. Okay, so this is the concept of divisibility. And intuitively it means we can arrive to n by taking steps of length, each of length m. Okay, let's see the first theorem about divisibility. It's a very important theorem telling us the properties of this operator, the divisibility, of this relation. It's a relation between integers. Okay, so what is the theorem? It says let a, b, c be integers. So choose any 3 integers whatsoever, a, b, c. then the following are true. Let's prove them one by one. So we want to prove first that if A divides B and A divides C, then A divides B plus C. Okay, so what does it say? If the integer A divides B and it also divides C, then A must divide the sum B plus C. So let's prove this. Okay, maybe I should give an example first. So suppose, for example, 4 divides 8 and 4 divides 24. Then 4 should divide the sum 8 plus 24, which is 32. And this is true, right? Because 32 is equal to 4 times 8. And this is true, and this is true, and this must be, so the conclusion must hold, my modest ponens. So let's prove it. So here is the proof. So we want to use, this is a conditional statement. It says P and Q implies R. So we will use a direct proof by, let's assume the hypothesis. So suppose that A divides B and A divides C. Now we want to show that A divides the sum B plus C. Let's see, what does it mean that A divides B? It means there is an integer K such that B is equal to K times A. So this is what we know from this. Now what do we know from A divides C? We know that there is an integer, let's call it L now, such that C is equal to L times A, right? So A divides B means we can reach B by taking steps of length A, and A divides C means that we can reach C by taking steps of length A. But the number of steps may be different, that's why for B we called it K and for C we called it L. Now, we want to show that A divides B plus C. What does it mean that A divides B plus C? So let me write it in red. So we need to show that this means that there is some integer, let's say n, such that B plus C is equal to n times A, right? So we need to find some integer such that B plus C can be reached by taking steps of A. So let's start with the left hand side. So now let's take, remember this is our goal, to show that B plus C is equal to an integer times A. So let's start with B plus C. Now from 1 we know that B is equal to Ka, and from 2 we know that C is equal to La, so plus La. Now we can take L as a common factor and finish with K plus L is equal to A, but since K is an integer and L is an integer, then their sum is also an integer, let's call it N, and so we proved that B plus C is equal to Na, where N is an integer. Okay, so if B plus C is equal to Na, this means we conclude that A divides B plus C. Again, because A divides B plus C means that B plus C is an integer times A. Okay, so this is the first property. Property 1, if A divides B and A divides C, then it divides their sum. A divides the sum of B plus C. Let's take property 2. Okay, what is property 2? It says if A divides B, then A divides B times C for any integer C, right? Again, if an integer A divides B, then this integer divides any multiple of B. Okay, so let's prove it in a direct proof as well. So suppose A divides B, then B is equal to an integer K times A. Okay, we want to show that A divides BC. So let's start with BC, and we know from here that B is equal to KA and KA times C. Now I can take A as I can use what associativity and commutativity of the product operation on the integers to write this as A times KC. Sorry, we can write this as what do I have here? So we want to show A divides BC. Okay, yes, again we want to show that A divides BC. This means we need to show that BC is equal to an integer times A. So here we can write this as KC times A, and this is an integer, say L times A. So we showed that BC is equal to an integer L times A. Okay, and this means that A divides BC. Okay, so this is what we want to show. If A divides B, then A divides any multiple of B. Okay, an example of this, for example, 3 divides 6, then this is true because 6 is equal to 2 times 3. Now check that 3 divides any multiple of 6. So 6 times 4 is 24, say. So 3 divides 24 because 24 is equal to 8 times 3. Okay, so this is true and this is true. Now let's check the third property of the theorem. So the third part of the theorem, it says that if A divides B, and B divides C, then A divides C. So this is called transitivity of divisibility. Notice, what does it say? If A divides an integer and this integer divides a third integer, then the first integer A divides the third integer C. Okay, for example, let's take an example. So 3 divides 6, right? And 6 divides 36. Then the first should divide the third. And check that 3 divides 36 is true because 36 is equal to 12 times 3. Okay? Because we can reach 36 by taking steps of length 3, 12 steps. Okay, let's prove it. So proof. Again, we will use a direct proof. So suppose that A divides B and B divides C. Okay, A divides B means there exists an integer k such that B is equal to k times A. And from here, B divides C means that there is an integer L such that C is equal to L times B, right? Now what do we want to show? That A divides C. So which means that we need to show that C is equal to an integer times A. So now start with C. Now C is equal to LB from here. But B is equal to KA from here. So L is equal to K times A. Now we can rewrite this using associativity of product of multiplication as L times K times A. And since L is an integer and K is an integer, their product is an integer, and so this is equal to, say, M times A. Which means that C is an integer times A. This implies that A divides C, which is the desired goal, right? We showed that if A divides B and B divides C, then the first divides the third C. So this finishes this property. And before I stop, so let me just remind you quickly what we proved now, that if A divides B and A divides C, then A divides the sum. Second, we proved that if A divides B, then A divides any multiple of B. And third, we prove that if A divides B and B divides C, then A divides C, where A, B, C are integers. Okay, we are talking about integers. So remember that let A, B, C be elements in the integers. Then these three properties are true. Now using these three properties we can get an easy corollary. Remember, a corollary is a consequence of a theorem. What is the corollary? Let A, B, C be integers. Then if A divides B and A divides C, then A divides the sum of multiples of B and C. So M, a multiple of B plus a multiple of C for all M and N. Okay, for all M, N in the integers. Okay, again, what does it say? Suppose A divides B and it divides, okay, C, maybe. Okay, so suppose an integer divides, an integer A divides two integers B and C, then it will divide the sum of multiples of B plus multiples of C. Okay, let's have a quick example. Okay, so suppose say 3 divides 6, that's true, and 3 divides 12. Then you need to check that 3 divides any multiple of 6, so multiply 6 by 3, say 18, plus any multiple of 12, say 36. Okay, so check that 3 divides the sum of 18 plus 36.